is an introduction to atomics. We're going to go through a simple threading problem. We're going to talk about what atomics are, why we use them, and go on to the topic of ordering, which is something that Rust makes you deal with quite early on, as soon as you, well, immediately as soon as you start using atomics. If we've got multiple processes or multiple cores, then when we have the same memory being used by those two processes, you can get into trouble. Now, if this is what's happening, you're getting the value, changing it in some way, and then storing it back, and then process 2 deals with it after, then you've got no problem really. If process 1 finishes all 3 of those operations and process 2 finishes all 3 of those operations, then everything should work. But that's not how things happen. But the virtue of using multiple processes is that our tasks can get interleaved. So process 1 might get the value of X, then process 2 might get the value of X. Process 1 increments X, but process 2 doesn't know about that. So it increments its version of X. Then when process 1 stores its X, it then gets blatted over by process 2, which stores its version of X. So we lose one of those increments there. So X equals X plus 1 is not safe in a concurrent system. That's what that shows us. And we could fix that with a lock. For example, say we had a bank balance, we might lock that bank balance and then load it, increment it, store it, and then release that lock. But what if we didn't have mutexes, so we couldn't lock that data? Or indeed, how would you even write a mutex? What would that even entail? Our original problem was that we had a load, a modify, and a store as 3 separate operations. And what we really want is a single uninterruptible operation, an atomic operation. Definition of atomic. It's a useful name, but it's not immediately intuitive unless you know that atomic is pertaining to atoms, which comes from Greek atomos, uncut, unhewn, indivisible. And that indivisible is the bit that's important to us. What it means is that no other thread will be able to see the state of a system partway through an atomic operation. Instead of having those multiple operations, we're going to replace it with a single operation, and that's the atomic operations that we have. And usually when we're talking about atomic operations, we mean at the hardware level. Now, does that mean that all CPU instructions are atomic? Is write always atomic? And the answer is not always. Just because it's a single instruction does not mean that it's necessarily atomic. So on x86, a 32-bit move instruction is atomic if the operand is naturally aligned, but non-atomic otherwise. Now, that doesn't necessarily mean a whole lot to lots of people, but what it essentially would mean is there is no guarantee here. You can't just make assumptions. It will vary from platform to platform. There's another instruction, store register dual immediate, which is not necessarily atomic on all platforms. So you can't just assume if it's a single instruction, it's definitely atomic. So how can we make sure that our operation is atomic? Well, we're going to use the wise folks writing the Rust compiler who have implemented a type for us that's going to limit itself to only using atomic operations where possible. So for example, we could have a counter, which is an atomic size, atomic use size, and then it provides operations such as fetch add. So we're no longer doing this load, modify, store. We're doing a single fetch add operation, and we're going to get onto what that means later and what the ordering entails. So you have things like this thing we talked about earlier, is that this x equals x plus 1 is probably not atomic. Maybe it is after the compiler's optimized it, who knows, but you're really rolling the dice there. What about x plus equals 1? Maybe. Plus plus x, possibly. X plus plus, who knows? There's no guarantees when you're writing that, but fetch add will be atomic. In Rust, we're limited in our atomic types to these here. So the various size of integers and unsized integers, a Boolean, and a pointer type. And for most things, that is kind of all you need. And the reason that it's restricted in types is that not all types, the operations you could do on it would make sense to be atomic. So it cuts you down to just the things that the Rust is able to say are atomic, have these atomic operations on them. And the operations that you have will vary slightly by type, but for an unsigned 32-bit integer, you have these operations here: compare exchange weak, fetch add, fetch and, fetch max, fetch min, get mutable, and various other ones. The ones we're going to be using are swap and load are the two ones, and store going to be the main ones. But it's nice to know that there's these other operations available as kind of a quality of life improvement. So to get started, we're going to implement a SpinLock. Premise is we're going to use an atomic bool to lock some data. Here we've created a struct, and we're using that atomic bool to lock our data. The value is going to be stored in an unsafe cell, and we're going to put a float in it. We could have used a generic type here, but just for convenience, I'm just using a float. And after the SpinLock, we'll be able to lock a value which isn't atomic, like our float, and then unlock it to safely modify. Now, just to re-emphasize, do not write this code, do not use this code, but hopefully it's going to demonstrate some of the usage of atomics and how they work. So to implement a SpinLock, we're going to split it up into these parts. We're going to implement a lock method, which is going to try and lock the data and then return a lock guard when it succeeds. We're then going to implement a SpinLock Guard, which is going to provide access to the underlying data and unlock that data again once the SpinLock Guard is dropped. And then once we're happy that that's going to work, we're going to allow this to work across multiple threads using the sync trait. And then just the quality of life improvement, we're going to use deref and mutable deref traits to make the SpinLock Guard more friendly. And then finally, we're going to talking about the lock method itself and the ordering, which we're not going to touch on at the start. We're just going to pick an ordering and then come back to what that means. And that's where I'm hoping to open it up for discussion. So let's do that now. Let's start by looking at a bad method of locking. Here, what we're doing is we are having a naive SpinLock Guard. A naive lock on our SpinLock, which returns a SpinLock Guard. So we're going to try and load our value of locked, which was our atomic bool. That load is totally atomic. It's totally fine for us to do. We can load that data. But the problem is when we load that data, it's correct, it's unlocked. But then when we come to store locked, someone else might have stored locked in. If we wrote this code, it would look like it worked for a long time. And then you would end up with two people locking the same data and modifying that data because we've given them access to it. Because we put that data in an unsafe cell, we're throwing caution to the wind a little bit, in the sense we're basically telling the compiler to trust us that we will protect this data. So then we can end up with a position where we're trying to have two separate cores or separate processes accessing the same data and manipulating it in some way, potentially getting us into all sorts of trouble. You could have one thread partially write it and the other one partially read it out with that kind of half-baked state, which would not be good. So again, here, there's this idea of an atomic operation is something that can't be divided in two. But that doesn't mean, if you have two atomic operations, you've obviously got something that can be divided in two. There's a gap there, there's an opportunity for other threads to interrupt. Instead, what we're going to use is we're going to use a swap. And the reason a swap's going to work is because we are doing the check and the store as one step. I mean, we're not actually even checking it. The idea here is what swap does is it replaces the value in locked with your value here, which is locked, and it returns out the old value. Because this is in a while loop, remember this locked, unlocked, locked is just true in this case, and then unlocked is false. So it's while true, because every time if we try and swap the value, it's going to return the old value. So while the old value was locked, keep putting in the new value of locked, but keep doing that until the old value was unlocked. Because when the old value was unlocked, that means you can be the only one who's locked it, but we've done it as a single operation. We've set locked in at the same time, which means we know that we've now locked it. We're the only one who's done it. And that means we can go and return the SpinLock Guard. And we know that our SpinLock is now locked. we're allowed to pass out the SpinLock Guard. We're allowed to give access to that data to whoever's tried to lock it. We could also have used compare and swap, or not compare and swap, actually, you'd use compare and exchange, because compare and swap is deprecated, I think. So we could have used compare and exchange instead of swap. That would just have given slightly more convoluted code, I would say. And it also, from what I've heard, would also incur potential performance hits. These will be very, very small performance hits. By virtue of the nature of the operation, you're locking it during that comparison and then swapping it out. And we'll talk about what locking means in this context a bit later on when we get on to ordering. So now we can get on to implementing a lock guard to provide the access to the underlying data. We stored that data in an unsafe cell, and that allows us to basically pass around references to the data easily using get, but it has to be unsafe. But we're making it safe by virtue of the fact that we are controlling it with our SpinLock. So we're only providing access to this data through our SpinLock. So this unsafe block is basically made safe by us, by our logic. That's kind of what the unsafe keyword means, is it means I've thought about this code and I know that it stands up to scrutiny in terms of who owns, that there's only ever going to be one mutable reference out at any one time. In this case, there's only ever going to be one immutable reference out there as well, because we've locked it the same for both read and write. So here, so we've got our SpinLock Guard. It's going to hold a reference to the SpinLock itself, which is the thing that has the data on it. And we're going to have two methods on it, get and get mutable, which are just going to return a reference to the underlying float in our case. I've written int here, ignore that. To the underlying float, either mutably or immutably, depending on which one we've called. And the way we generate this SpinLock Guard, actually we'll come on to that in a second, well, actually we've seen it, the way we get that SpinLock Guard is by calling this lock method, so we know that at that point it's totally ours, we're the only one who are going to have a SpinLock Guard. Once we're done with the SpinLock Guard, we want to make sure that we unlock the data. So that's where drop comes in. This is the equivalent of a destructor in C++. And all that needs to do is call store unlocked. Once it calls store unlocked, any other threads that we're trying to access that locked data will be able to. One of them will be able to anyway, and then they can carry on. But while we have the lock, we're the only ones who can access it. So if we're happy now that this works, which hopefully we are, then we need to allow it to be passed around, to have a reference to it be passed around on multiple threads. And unsafe cell is not sync inherently, because it provides no protection against data races, because it allows unsynchronized shared mutable state, which is a big no-no in multi-threaded programs. I mean, in general, but especially in multi-threaded code. So, but we know that we've ensured that our SpinLock is safe to share because we've added this locking behavior. So no one's going to have access to the value unless they've locked it. So because we know that, we can now use unsafe impulse sync for our SpinLock. And what that's going to mean is that we've said, trust me, compiler, this is sync. I will make sure that concurrent access is safe, which we've done through our locks. And then as a final kind of quality of life improvement for this bit, we're just going to use the deref and mutable deref traits to make the SpinLock Guard more friendly. So those are exactly the same as our get and get mutable methods, apart from all they mean is that now I can just use dereferencing to get the value out instead of having to call some special method. So that's our SpinLock. Whistle stop tour, very fast. But we want to improve it, / look for why there might be problems with it. And for that, we need to look at ordering. In the methods we've used so far, the ordering we've done, we've just been putting relaxed. Maybe we didn't know what it meant. Hopefully we will by the end of this session. And that's what's kind of nice about Rust and not nice about Rust is if you want to use atomics, it will force you to pick an ordering. And that means you're going to go to look into ordering and then try and figure out what it means, which is useful. I found it a bit headbendy, but hopefully it'll make some sense. The reason we need to think about ordering is because for two reasons. The first one being the fact that the compiler can reorder things. So our code might say x equals 1, y equals 3, x equals 2. But the compiler sees that and says, do you know what? I'm not going to bother setting it to 1. I'm just going to set it to 2, and I'm going to do that first. I'm going to do that before I set y equals 3. So the order of events in our single thread of code is not consistent. It's not what we wrote. It's not what we wrote down. Now, in the case of single-threaded code, the compiler is going to look and only make changes that won't affect the result of the code. So, if you did x equals 1, y equals x times 2, x equals 3, it's not going to reorder x equals 3 to be before y uses x, because it can see that would have an effect on the code. The end result would be different. It's not going to do it. But in multi-threaded code, it's very hard to see if this is shared mutable state that other threads would have access to. It's very hard for the compiler to tell what optimizations it can make, what optimizations it can't make. So up until C++11, there wasn't really an easy way to stop these things happening beyond something like the volatile keyword, which indicates that values can change underneath. Therefore, please don't optimize this too heavily. And those are the things that work a bit, but they don't help with a lot of other things. For example, hardware reordering. So even if the compiler doesn't reorder it, that doesn't mean that the code, when it's running on our multiple threads, is going to see values in the order that it looks like we're going to see values. So if we have an initial state, x equals 0, y equals 1, our thread 1 might set y to be 3 and then x to be 1. And thread 2 will then say, okay, well, if x is 1, multiply y by 2. There are multiple outcomes of this code by virtue of the fact that it's multi-threaded. It's not obvious how things are going to happen. So, for example, if thread 2 checked before thread 1 had completed, then we would get y equals 3, because thread 2 would never modify the value of y. If thread 2 did the check after thread 1 had completed, y is set to 3 by this point, and x is set to 1, which means y does get times by 2 and it becomes 6. But we could also get y equals 2, which would mean thread 2 saw that x equals 1, because even though we might not have reordered these operations at the compiler level, the operating system might not have synced up that value of x. So thread 2 might not know that y is 3 yet. It might only think that y is still 1, but it might know that x is 1, which is a little bit odd. So then we have, well, x is equal to 1, but y is still equal to 1. We haven't actually changed it yet. So if I multiply it by 2, it's still 1 at the end of the day. So when I double it, it just becomes 2. And then even though we might have set y equal to 3 on thread 1, thread 2 can then overwrite that with a 2, which is kind of confusing, because you would think that it would either be that thread 1 would overwrite it with the 3, or thread 2 would be setting it with 6, but that's not necessarily going to happen. At this point, it's good to kind of introduce an image to have an idea of what's causing this weird hardware reordering, when a thing's happening. And it comes down to the fact that CPUs are complicated, hardware is complicated. There's a lot of stuff going on. So if we had a multi-threaded system and it was all accessing the same kind of shared data in the main memory, that would be really slow. You have a choice with your hardware. It's either simple and slow or complicated and fast. It feels like those are your two options. And generally they are complicated but fast, and that's through being heavily cached. So even though in this bit it looks like both threads are accessing the same underlying state of x and y, which might be blocks of memory, they're not accessing that from the main memory. They're accessing it from some cache in between. And then the hardware, the manufacturers will have set up some cache synchronization to make sure that if core 0 changes a value, that core 2 will pick up that value in some mechanism. And it's depending on whether you're using ARM or whether you're using x86 or whether you're using anything else. That synchronization is going to be different. What guarantees are made about when updates will be made to other cores, caches of values is going to be different, which means we can't make any of those assumptions that we really want to make in our multi-threaded code to make it make sense. And what's more, until we got atomics, we had no way to communicate what we were even trying to do or what was necessary for those updates. So as I mentioned, depending on the hardware, we get different guarantees about what can and can't happen. x86 provides strong ordering guarantees. Someone on the call might know. I don't know if that's forever guaranteed. Is that just for now? Will that change? And ARM provides weak ordering guarantees. So you're going to get more of that reordering. And you might have code that works on x86 and then doesn't work on ARM as a result of these discrepancies. And when we think about Rust, we think of it as being really, really good at being pretty agnostic in lots, wherever it can be. And so this could really mess up your code. And you'll end up with bugs that are really hard to track down. So that's why these ordering things are introduced. We have 5 orderings in Rust: relaxed, release, acquire, release, and sequentially consistent. We're going to go through those now. Hopefully they'll make a bit of sense. I don't know if I've said already, but I am not an expert in this by any means. So if anyone wants to jump in if I make any mistakes, please do. And we'll have loads of time for discussion at the end. So don't worry. Relaxed, if you look at the doc in Rust compiler, it says no ordering constraints, only atomic operations. This corresponds to memory order relaxed in C++20. All of those memory ordering, the relax, release, acquire, release, sequential consistent, those are all taken from C++, specifically C++11's memory model, and in C++20 is the latest, with all the kind of modern things. And I would really recommend, if you're reading up on this, to use the C++ doc, because it is good. So for the remaining definitions in here, I'm going to use the C++ ones. So in CPP reference, it says there are no synchronization or ordering constraints imposed on other reads or writes. Only this operation's atomicity is guaranteed, which is essentially saying the same thing. So it doesn't change the fact that your operation is atomic. If I've said I'm doing a fetch add, I am doing a fetch add. It will retrieve that value, add to it, store it back, and that won't get interrupted. But I can't rely on that happening before or after something else. I'm accessing it from another thread. And maybe that's not a problem. If I'm just incrementing a counter, then I can increment it, you can increment it. When it all gets synced back, it should be fine. As an example of relaxed ordering, if I start with y equals 0 and x equals 0, this is very similar to the earlier example, but taken off of CPP reference. I'm setting R1 to be the value of y. I load it in. Then I store into x the value of R1, set x to R1. And then on another thread, I might set R2 to be x, and then set y to be 42. And somewhat surprisingly, although not surprisingly based on what we've already seen, R1 can equal R2, which can equal 42, because what can happen is y can get set to 42 before R2 gets loaded. And then that would mean that R1 would get set to 42, x then stores R1, and then R2 loads it. So we basically switched the orders of the operations here, which we're allowed to do because the memory order is relaxed, and because storing 42 into y before doing R2 equals x load is not going to have any side effects within thread 2, but we don't realize that there's thread 1 going on at the same time, and we've said memory ordering relaxed, so there's nothing stopping that happening. So the other orderings we have, so release Again, this is taken off of CPP reference. It means a store operation with this memory order release, will perform the release operation. The result of that is that no reads or writes in the current thread can be reordered to after this store. So that would have fixed our case before, where we wouldn't be able to reorder the writing of R2 to be after a release store. It also means that all writes in the current thread are visible in other threads that acquire the same atomic variable. And when I say acquire, I don't just mean load, I mean load with acquire ordering. And writes that carry a dependency into the atomic variable become visible in other threads that consume the same atomic. The consume is unrelated to, in Rust, we don't have the consume ordering. So we're just going to skip over that bit. I don't know anything about consume ordering. If anyone else knows, please feel free to weigh in at the end. And then you have acquire ordering. We've already touched on it on the previous one because it was the counterpart. When we have acquire ordering, so a load operation with this memory order, so for doing a load operation with acquire, that means it's going to perform the acquire operation. The result of that is that no reads or writes in the current thread can be reordered to before this load. So if I'm doing some read or writes after this, it won't move them to before. And it means that all writes in other threads that release the same atomic variable are visible in the current thread. So if thread 1 has modified X with release, then thread 2 that gets it with acquire will definitely pick up that change if it's happened before it. But that wouldn't be true if you hadn't set one to release and one to acquire. They have to be there as a pair, otherwise your guarantees are lost. So to show you what this looks like in some C++ code, we have this atomic pointer to a string and some random data. We create a new pointer to a string and set some data, and then we store into our atomic global pointer value of p with memory order release. This is the equivalent of ordering release in Rust. We have a consumer, we create a pointer, and then when the pointer is not null anymore, so this is basically means that it's waiting until this has been assigned to, which happens at this point. It's going to spin. Once it's been assigned to, it can then check that the value in it is definitely hello and that the data is definitely 42. And it can do that because release meant that the this data equals 42 couldn't be reordered to after that store, and the acquire means that we definitely are going to pick up that that release from the pointer store. The acquire is actually probably less important here. And so when I execute those two things on different threads, we're never going to get these asserts firing. The code's going to work, and that wouldn't be true if we had relaxed ordering. Sometimes they might fire because we haven't guaranteed any ordering. In reality, we might never see this. We might run it 50 million times and never see these problems. But the problem is that you can sometimes get these problems, and when you do get them, they're going to be really, really hard to figure out. Similarly, there's acquire release. So this is a read, modify, write operation. We'll do both the acquire operation and the release operation. So this is just a combination of the two. And this is something that you might want to do if you were doing like a compare and exchange, where I needed to have my check be able to pick up all of the changes in the right order, but then I need to store it back, and I need to make sure that other threads pick up those changes. So no memory reads or writes in the current thread can be reordered before the load nor after the store, and all writes in other threads that release the same atomic variable are visible before the modification. The modification is visible in other threads that acquire that atomic variable. So it's just the same as the two previous ones, but combined for those cases where you might be doing a read, modify, write. And then finally, there's this sequentially consistent case. And this is the one that I think in the Rustnomicon, it says, if you don't know what you're doing, use this. And the reason being is that a lot of those problems that we saw with the other cases that you have to think carefully about, this basically locks down a lot of the optimizations that can be done and will incur a performance hit, but it will potentially avoid some of those issues. So this means that a load operation will perform an acquire. So this is exactly the same as acquire there. A store operation performs a release, the same as the release one, and a read, modify, write performs both an acquire and a release. This is in the Rust case. For C++, actually, I need to confirm that. But you also get that a single total order exists in which all threads observe all modifications in the same order. And that's a pretty big restriction to put on your hardware and to put on your compiler, but that's what sequentially consistent does. And it's very rare that you would actually need it to be sequentially consistent. But if you do need it to be sequentially consistent, this exists, or if you don't know what to put, it's safer. It's not going to have some of the confusing issues. But if you find yourself needing it a lot, it's probably worth raising the question, should I be using atomics here? Is this the right solution for me? Am I creating code that's too complicated to maintain? Maybe I'd be better off with a mutex. Yeah, so those are the different options available to you. As to whether or not to use atomics at all, or at least whether to use atomics on mutexes, if multiple threads concurrently access a mutable variable, then all threads have to use atomic operations to read or write to it, or they could use mutexes. So you have to use something. If you're using multi-threaded code, and Rust won't let you not use something unless you try really hard. But if you're going to use something, make sure you're using it as properly as you can. So that's all I had in terms of slides. I feel like we've probably got a lot of discussion we can have. I hope I've done my best to try and explain things. The conclusions there are that atomics are a bit subtle. Memory is weird. Time is an illusion. Like, things don't happen in the order that you think they're going to happen. I've got a bunch of links as well that I'll put in the chat. Because the C++ resources on this are great. I've copied a lot of the examples from the 1Password chat, from the Crest of Rust video, 1Password video, CPPCon's video. The other thing I want to mention is there's a book coming out at the end of the month that I want to read but haven't read because it hasn't come out yet. When I read that, I might find that there's things in this that I would have done differently or that I would want to change. So maybe we'll do another one on this in the future. But that's Rust Atomics and Locks by Maribos, who is one of the leads on Rust compiler. But there's also the Rustnomicon Atomics chapter, which is very short. There's also just some various other links I found. Someone talking about SpinLocks being harmful if you're ever being tempted to use a SpinLock for real. Refreshing has a blog on atomic versus non-atomic, and also a video how Ubisoft developed games for multi-core, and then talking about the introduction of C++11. And I found Rust Brazil had a link for understanding atomics that I found quite useful to try and understand it. See someone's put in the chat. I'm going to put up the chat now so I can actually read it. Concurrency in action, someone's recommended for C++11, which, yeah, like I say, this is all based on C++'s model for it. So yeah, it should all definitely still hold. Yeah. Shall we, go to discussion? Anyone got any thoughts on it, or anything anything I said wrong? Any mistakes? Oh, everyone's gone quiet. The chat's nice and active though, so I'll just pick up things in the chat. So yeah, so Christoph recommended C++ concurrency in action. There's a link to that. Yeah, compare and exchange being CPU's atomic instruction. It is, I think it's different as well, depending on the architecture, what that will entail. In the Crest of Rust video, he talks about how I think it was on ARM, there's basically a little spin inside to implement compare and exchange, where one tries to, you have it's basically split into two operations, where one tries to read the value, then the next one tries to write it, but only if the read is still the same. So it might succeed in reading the value that it wants to then swap out, but it won't necessarily be able to write. And if it can't write, then it will have to spin until it can next write. So it can still sometimes fail. But yeah, there's a whole load of subtleties with different hardware, and I felt like there's everything I read, I felt like there was more to read, and it's very hard to test, which is normally how you try and learn stuff. Is you're like, oh, I'll just see what happens, I'll just implement it. But these are the kind of things which are going to be bugs that will happen 1 in 50,000 times. So all I felt like I had was reading reading the docs and trying to understand it as much as possible. Oh, someone recommends video implementing a hazard pointer. Oh, I'll check it out. I haven't seen that. Yeah, and I feel like as well, coming from a writing Rust background, Rust holds your hands through a lot of mistakes, but it doesn't with atomics and threading problems like this. If you're using atomics, it can't reason about it, so it can only do so much for you, beyond which you have to know yourself. And then because it works like, say, 9,999 times out of 1,000, maybe you'll think it's working, and then you'll end up with a bug that happens 1 in a million times. And will you fix it? I don't know. Maybe you'll just hope it doesn't happen again. Yeah, Matt makes a good point. Unless you're implementing lock-free structures yourself, then you should be sticking to higher level tasks as much as possible, which is, yeah, totally true. This isn't something that you want leaking into regular code. It should be as isolated as possible. Yeah.
So funny enough, at my current work, we are doing some of the multi-threading when we're performing encryption, just to be as fast as possible, right? So we had to implement some of that ourselves, and we had a bug in our code. So we are writing C++ cross-platform, and some of the unit tests were showing us this bug, but it was only failing on Linux from time to time. So, you would run the tests hundreds of times, and then one of these times would fail on Linux. It would still work on macOS and Windows.
Mm-hmm.
And for a time being, we kind of ignored it. But then one of the customers just said, oh, there is a corruption of something, right? And that was like, oh, that might be this. And it all came down to the scheduler of how the operating system, scheduler on the operating system worked, and differently on Linux, right? And this one was just showing to us that, yeah, there is a problem. But yeah, if we were, so that was helpful, because then we could just cycle the test on Linux, and as long as we fixed the Linux, so we were like running that 1,000 of times, and then it was showing once in that 1,000 of times, right? So like when we were fixing it, it was kind of a good indicator if we were on a good path or not. But yeah, writing the multi-thread code is difficult, right? And yeah, you think like, oh yeah, let's multi-thread that and that, and you also need to do lots of performance testing, right? At that time, to really prove, oh, is it faster, right? Because at some point you're blocking as well, you're mutexing, whatever, right? So is it really faster than doing that somehow? Yeah. And again, you could just parallelize that, right? Maybe if you have trivially parallelized tasks, you just split it, let all the other tasks to do the work, and threads do the work, and then maybe join at the end, right? So fun out and then eventually fun in, without all the nitty hacky thing of synchronization. Yeah,
Exactly. If you could simplify it, if you could make your code single threaded without taking a performance hit, why wouldn't you? Because take whatever chunks you can simplify, and just and then that way you can focus your energy on the bits that are inherently have to be multi-threaded to get the performance you need. Give them the undue attention, the attention they deserve, and make sure that you get this right first time. Because, like, say, that bug that you're talking about was reproduced if you ran it 1,000 times, but if it had been one where you could only reproduce it 1 in 10,000 times, your confidence that you've actually fixed it starts to drop. And it's quite hard to reason about. So yeah. just to mention as well, we have another meetup. Matt's kindly is agreed to do a talk, which I'm excited for, on the 30th of November, called Common Crates and Their Usage, where we're going to go through some common Rust crates. Yeah, so I'm looking forward to that. Most of you probably know Matt from previous meetups. He knows a lot of stuff, so it's going to be good. Looking forward to it. I think Alex,
stuff.
You know a lot of stuff. And then I think Alex was planning to do a December social, but I can't remember the details of that. I think he did a poll a while back, but watch out for the Discord. And if anyone's in Cardiff, then yeah, try and do a social. But we're also, yeah, looking for speakers. If anyone has a topic that they would be willing to talk about, it can be literally anything, or not literally anything, but anything related to Rust and C++, even tangentially. Can be on assembly, be on whatever you fancy, something you're working on. It doesn't have to be like a deep dive into a particular technical topic. It can be, yeah, anything at all. But yeah, we're always looking for new speakers.